So this video is about simulating a 3D double pendulum consisting of two 3D rigid bodies. Okay, so here is that object, a 3D double pendulum. Like we discussed in a previous lecture, there are lots of permutations and combinations of what joints you put here and so on. But here's perhaps the simplest version of a truly 3D double pendulum, where you have a rigid body, another rigid body, and we've made this a ball and socket joint and made this a ball and socket joint. Recall that a ball and socket joint means that translation of that point is constrained or prevented. There can be no translation of that point, but that joint does not constrain the rotation at all, so it can rotate this way into the plane or along this axis. Okay, so that's a ball and socket joint, as is this. So again, these 2 points, this point on these two rigid bodies need to be coincident, but they can rotate relative to each other however we want. Okay, so that's a double pendulum. How do we go about simulating something like this? Before you actually simulate something like this, what we need to do is to learn how to precisely define or describe a system like this. How do you describe a system like this that is in 3D? It is generally a bit more work than describing a two-dimensional system. Okay, the first thing to do is to define the rigid bodies. So what are the objects that compose this system? Those are the rigid bodies. In this case, the number of rigid bodies is 2. And then for each rigid body, J, so let's say J goes from 1 to 2 in this case. For each rigid body, of course, you define what the mass is. And then we also define the moment of inertia matrix. And most commonly, we will define the moment of inertia matrix in a principal axis frame so that the moment of inertia matrix is diagonal. Okay, so that's important. That's just a convenience thing. It's convenient to have a diagonal moment of inertia matrix, so we pick a body fixed frame that is that consists of principal axes, so that in that body fixed frame, the moment of inertia matrix is diagonal. Okay, so that's the first part. Number of rigid bodies, mass, moment of inertia. And then we define how the rigid bodies are connected to each other and or to the ground. Okay, how are the rigid bodies connected to each other or to the ground? So in this case, of course, it's just ball and socket joints, but we can sort of have more detail on that sort of dimension. Okay, so how are the rigid bodies attached? In this case, it's relatively simple, but we still have yet to define it in detail. But let's consider in general there are n rigid bodies. And then there is also the ground, right? So in this case, there are 2 rigid bodies and then the ground, which is, or the ceiling, or whatever you call it, the earth. So for at least these problems. So let's say there are n rigid bodies, n equals 2 here, and then the ground or the inertial frame is the n plus 1th object, right? So n rigid bodies plus 1, because we are considering ground to be an object as well. Okay. Then the first thing to do when you have such n plus 1 objects is to define whether two objects from those n plus 1 objects are connected or not. Okay. First thing, the simplest thing to define is to say whether something is connected to something else or not. Okay. So we usually do this using something called a connectivity matrix. Let's call it C, which is an n plus 1 by n plus 1 matrix, which defines whether object J and object K are connected together. Okay, so if the object J and the object K are connected together, then we say C of J comma K equals 1. Okay, if J and K are not connected to each other, C of J comma K is equal to 0. Okay, and then the diagonal elements C of J comma J can be 0 or 1. It doesn't matter. You can set it to whatever quantity you want. By convention, I'm going to use equal to 0, but really it's a quantity that we don't really use. Okay, so really all that we care about is C of j comma k, where let's say j is greater than k, so that all we care about is the upper diagonal part of this matrix, and the lower diagonal is a symmetric matrix because if j is connected to k, k is connected to j, so C of j comma k will be the same as C of k comma j. So the symmetric matrix, the diagonals don't matter, because what does it mean to say is object j connected to object j? Well, you can set it equal to either connected or not connected. It's not relevant to us. Um, in any case, so for this particular system, the connectivity matrix is this. Diagonal, like we said, we're just setting 0 by convention. This one says, so this is the 1 comma 2 element. It says object 1 is connected to object 2, right? Object 1 is connected to object 2. This is the 1 comma 3 element, which says object 1 is connected to object 3. Object 1 is just rigid body 1. Object 3 is the ground. So it says object 1 is connected to object 3, or object 1 is connected to the ground. That's what this says. This says, this is, what is this? This is 2 comma 3, this element. 2 comma 3 equals 0 says that object 2, or rigid body 2, is not connected to the ground, which is rigid object number 3. Okay, so that's the meaning of this matrix. So think about how to represent the system using these rules. Okay, so that's called the connectivity matrix. It's very commonly used in when you're doing simulations of more complex systems, like when you're doing finite element methods and so on. Anyway, it's a standard tool to convey what object is connected to what other object. Now, then once you have the connectivity matrix, for each connection, you have to define what kind of joint it is. Like we discussed, we can have various kinds of joints: ball and socket joint, hinge joint, universal joint, even rolling, sliding. Those things can also be treated as joints. So these are the options. Prismatic joint is another kind of joint.